So for a function of two variables, we've talked about two different integration concepts. One of these integration concepts was the double integral, which happens over some kind of filled-in region. And then last time, we talked about doing a line integral of such a function, which is an integral not over a two-dimensional region, but over some kind of one-dimensional curve. It turns out that there's a deep connection between these two ideas right here. However, in order to discuss this connection, we're going to have to talk about a type of function we haven't seen yet. It's worth pointing out that for functions of several variables, functions who have multiple inputs and a single output, well, they play a role right here in a line integral. But the actual act of parameterizing the curve itself involved a function, the curve, who took a single input time but spit out vector output. Now, all of Calc 1 was about functions who took a single input and spit out a single output. So amongst these three formulas here, do you see the kind of function who's missing? Functions who have several inputs but also have several outputs. What do these kind of functions look like? And why do we need to talk about them in order to see the connection between double integrals and line integrals? Well, let's handle the first part first. What do these functions look like? We've actually experienced this kind of a function already. Imagine we took some function of two variables, say the function x squared plus y. When we took its gradient, its derivative, we came up with a vector 2x comma 1. And if you take a look at it, this is exactly the proper form. Its input is a point in R2. Its output is a vector in R2. So every gradient we've ever looked at is actually a special case of a function from R2 to R2. Well, how did we visualize the gradient? Well, our idea was at every single point, say the point 0, 0, we would plug in 0, 0 into the gradient. We would come up with the vector 0, 1, and so we would sketch 0, 1. We could do that at every point. We could compute the gradient, say, at the point 1, 0. That would come out to being the vector 2, 1. So at the point 1, 0, we would use this as a tail for a vector who goes 2 units over and 1 unit up. If we took the gradient at the point 1, 1, we would get the vector 2, 1 as well. So at the point 1, 1, we'd get a vector who goes 2 units over and 1 up. If we were to repeat this for many, many more sample points, then we would get arrows at every single point. Such a picture is sometimes called a flow diagram or a flow field because it seems to describe the motion of some kind of a particle through some sort of a medium. For example, if we had a point right here, it would be moving up. If we had a point over here, it would want to move sort of out this way or out this way. In physics, these are sometimes called force fields because we can think at every single point in the plane there is a force acting on that point, pushing it in a certain direction. But in mathematics, we're just going to call these things vector fields. And so that's the missing type of function. So a vector field is a function of the form f whose inputs come from Rn and whose outputs are in Rn. So such functions would have many inputs. Let's say take the case when r is equal to 3. And then outputs would be vector valued. So there might be a component f1 of x, y, z, and then a component f2 of x, y, z, and a component f3 of x, y, z. Or we can also stack the outputs vertically as f1, f2, and f3 evaluated at the point x, y, z. We visualize a vector field by taking the space Rn, and so again, right now I'm drawing R3, and then at every point in space, say at the point x0, y0, z0, we attach to it a vector, and the vector we attach to it will be the vector f of x0, y0, z0. So at some different point right here, there might be a different vector, and at some third point, there might be some third vector. And so what we would do is for every single point in Rn, we would go and plot the corresponding vector. And this would give us a way of visualizing this kind of a function. Of course, the only place where mere mortals could plot a vector field is in the plane, and so let's take a look at that. Let's plot the vector fields f of xy equals x comma y, and g of xy equals negative yx. Let's focus on this vector field first. So I'll give myself some axes to play around with, and then I'll start plugging in points. For example, at the point 1, 1, we would get the vector 1, 1. So at the point 1, 1, I'll draw a vector who goes 1 unit over and 1 unit up. At the point 1, 0, we would get the vector 1, 0. So I draw a vector who goes 1 unit over, 0 units up. At the point 0, 1, we're going to get the vector 0, 1. So at this point upon the x or y axis, we'll draw a vector who goes up 1. At the point 0, 0, we're going to get the vector 0, 0. Now the vector 0, 0 is a vector who doesn't point, so we usually just draw it with a thick dot. And so if I repeat this at every point, we would eventually get a picture who looks something like this. And so we get the idea of a vector field or a flow field where everything radiates outwards from the origin. And the farther a vector is away from the origin, the longer the vector gets. For comparison, here's a computer-generated image of the exact same vector field. And you can notice two main differences between me doing it by hand and me doing it on a computer. One is the sheer number of points. The computer will routinely plot hundreds and hundreds of points to get a vector field, so you get a much better sense of the flow. However, notice that here at the point 1, 1, the arrow is supposed to be 1 unit over and 1 unit up, and that's clearly not what we're seeing right here. In order to pack all of these arrows into one picture, a computer will very often scale them down. So whereas the general idea that arrows get longer the farther away they are from the origin, their actual length is not well preserved in a computer plot. So keep that in mind. You can check the general structure of the vector field and the relative size of the arrows, but not absolute lengths. For comparison, let's focus on the second vector field. So we'll go and give ourselves some chorded axes, some space to plug in values, and let's start churning our way through. So for example, at the point 1, 1, we're going to have the vector minus 1, 1. So a vector who goes left 1 unit and then up 1 unit. At the point 1, 0, we're going to have the vector 0, 1. So a vector who points straight up. At the point 1, minus 1, we're going to get the vector 1, 1. So at this point, we'll go 1 unit over and 1 unit up. At the origin, we're going to get the vector 0, 0. So we'll still have a big fat dot there. And then we can continue on. And we get a picture that looks something like this, where we have the idea of shapes rotating counterclockwise, spiraling away from the origin right here. Again, for comparison purposes, here's a computer-generated plot of the same thing. Notice that it's pretty consistent with our picture. We have the notion of going around counterclockwise around the origin, although with the added bonus of having many more points to plot, I do get the impression that the flow is actually sort of circling around the origin as opposed to spiraling outwards. Now, that's the benefit of being able to plug in 500 points as opposed to 25 points. So suppose that we had a vector field, say of two variables, f of x, y, and so it has two components, f1 of x, y, and f2 of x, y. We could ask all of our sort of basic calculus questions. For example, when is f continuous? When is f differentiable? And the related question of if it's differentiable, what would be the proper derivative concept? And then the flip side, what do we integrate f over? What kind of integrals will we have for a vector field? Well, we're going to try to answer all of these questions in one podcast because we're simply going to build off of topics we already know. For example, let's focus on the question about when is f continuous. F is sort of a combination of two different types of functions. On the one hand, it's a vector-valued function that has two components. And when we talked about vector-valued functions, we discovered that vector-valued functions were continuous if each one of their components were continuous. But notice that each one of the components is a function of two variables. And we spent a lot of time learning about what it takes for a function of two variables to be continuous. And so, let's combine these two ideas together. We're going to say that a vector field is continuous if each one of its two component functions are continuous as functions of several variables. And so we've answered our first question. Vector fields are continuous provided each component is continuous as a function of two variables. All right. Well, on to the next topic. When is a vector field differentiable? Well, again, just think about what we had done before. For a vector-valued function, the argument was that a vector-valued function, like a curve, was differentiable if each of its components were differentiable. And since each one of the components is a function of two variables, we know how to check for the differentiability of each of the components. And so, just like for continuity, When is f differentiable? Well, a vector field is differentiable if each component is differentiable as a function of several variables. Alright, let's hit the next topic. What should the derivative of f be? Well, when it came to vector-valued functions, the quote-unquote derivative of a vector-valued function was done component-wise. So we took the derivative of the first component, and we took the derivative of the second component. That was how we handled vector-valued functions in some of the earlier topics. However, when we talked about functions of several variables, the derivative concept wasn't a prime, but a gradient. So if we were to combine these two concepts together, we would have a derivative who is a vector whose first component was the vector gradient of f1, or f1x, f1y, and whose second component was the gradient of f2, f2x, f2y. If you just take a look at this thing, you have a vector whose rows are vectors. Well, why not just take out all of the extraneous symbols? And what you'd have is a matrix whose first row was the gradient of f, and whose second row was the gradient of g. So you're differentiating each row separately using the correct derivative concept. And in fact, this is what the derivative of a vector field is. We're not going to use the prime notation, though. Instead, it's traditional to use the letter capital D to denote the derivative of f, and this is sometimes called the matrix derivative of f, or the Jacobian matrix of f. And so now we have an answer to our third question. What is the derivative of a vector field? Well, the derivative is called the derivative matrix, and it's a 2x2 or 3x3, or in general n×n matrix of partial derivatives, where each row is the corresponding gradient of that component function. We'll get to the integration question in just a second. But what I'd like to point out is that we've actually had some experience with this Jacobian matrix hidden behind the scenes in some of the things we've already done. For example, suppose you had a function of two variables. Then we could take its first derivative, which is called the gradient, and we would have a vector whose first component was the partial derivative with respect to x, and whose second component was the partial derivative with respect to y. This is now a vector field. It's the very first kind of vector field we ever saw. So we could now go and take the derivative of the gradient of f of xy. The derivative of the derivative of f, the second derivative. Well, the second derivative is going to be a matrix whose first row is the gradient of the first component. So the partial derivative of fx with respect to x, and the partial derivative of fx with respect to y. The second row of the derivative matrix will be the gradient of fy. So fy's derivative with respect to x, and fy's derivative with respect to y. And so this matrix right here is quite literally the second derivative of the function f of xy. Do you recognize this matrix? It's precisely the Hessian matrix we needed in something called the second derivative test. So there's an honest-to-God reason why this is called the second derivative test. This is what the second derivative of a function of two variables has to be. Another question related to derivatives in vector fields is the following question. When is the vector field the derivative of some other function? Because remember, if we had a function of two variables, then the derivative is nothing more than the gradient. If we were to say, take a look at our first function that we plotted, this function right here, f of xy equals the vector field xy, is this the gradient of some function? That is there some function f of xy such that the gradient of f is equal to the vector field f? So remember that the gradient of f is simply fx fy, and we would like that to be equal to x times y. Or we would like the derivative of f with respect to x to be x, and the derivative of f with respect to y to be y. Could we find a function who had these properties? If I focused on this first equation, that should mean that the function f should be the antiderivative of x with respect to x. So if we work this out, we're going to get 1/2 of x squared plus a constant. But that constant could be anything that involves the letter y. So what we know right now is that this function must look like 1/2 x squared plus stuff that involves only y. However, if we focus on the second equation says that f should be the antiderivative of y with respect to y. That means that it should look like 1/2 y squared plus anything that did involve y, so stuff with x's. Could you put these two things together? Could we find a function who satisfies both of these statements at the same time? Well, if we piece everything together, this tells me that the function f had better have a term that looks like 1/2 x squared, and it needs to have a term that has 1/2 y squared in it to make these two equations happy. And if I look at this formula satisfies the orange equation because it takes the form 1/2 x squared and the remaining things involve only y. It also makes the second equation happy because it has a part that looks like 1/2 y and the remaining things are stuff in x. And so here is a function whose gradient is exactly this vector field. And we could double check it very quickly. If we take the gradient of f, you might notice that if we took the level sets of this function, 1/2 x squared plus 1/2 y squared equals to a constant, that's the same thing as x squared plus y squared equals twice a constant, which means the level sets should be concentric circles. And if I notice, every single one of my vector field vectors appear to be at right angles to them, so they're satisfying the property that a gradient should have. What about the green vector field? Is there a function g of xy such that the gradient of little g is the vector field capital G? So the gradient of little g would have to be g sub x, g sub y, and it would have to match minus y, x. Well, that would mean that the partial derivative of g with respect to x is negative y, and the partial derivative of g with respect to y is x. So let's just integrate these two statements. Taking the first statement, the function g should be the antiderivative of minus y with respect to x. So that means we're going to get the function negative xy plus stuff that doesn't involve the letter x, so stuff with y only. On the other hand, since the partial derivative of g with respect to y is x, if we integrate x with respect to y, we should recover g. But the integral of this will be xy plus constants with respect to y, which means anything that has an x. Is it possible to find a function g who makes these two statements happy? But if you think about it, this equation right here doesn't satisfy this part right here. It doesn't look like positive xy and leftover stuff in x's, and this equation right here doesn't make this equation happy. And so it looks as though you can't find a value g who satisfies these two equations. But it seems to be only based on my inability to make the two equations happy. Let me see if I can give you a second reason for why this shouldn't be a gradient. Imagine drawing what the appropriate level curves would be. What are the lines who appear to be orthogonal to all of the vectors we've drawn in each one of these pictures? If there were level sets to be had, would look something like this. Now remember, what is a gradient supposed to do? Well, it would say that if we were to say start on this particular level set, the gradient is pointing upwards, so this moves to a higher level set. And then this will move to a higher level set and a higher level set. And so as I work my way around, I'm moving up to higher and higher level sets. But notice that they work their way around, and so eventually I come back to the same level set I was on before. And so we've just shown that this level set, the positive x-axis, is at a level set higher than itself, and that's just stupid. So I have lots and lots of evidence to suggest that this particular vector field is not the gradient of some function. And I can go one final step and give a conclusive test. We have the so-called gradient test. If a continuously differentiable vector field f of x, y, z does not satisfy all three of the equations del f1 del y equals del f2 del x, del f1 del z equals del f3 del x, and del f2 del z equals del f3 del y, then it cannot be the gradient of a function. Now this has been stated in terms of functions of three variables right here. If you had a function of two variables, then simply strike out all of the references to the variable z. So for a function of two variables, unless it satisfies the two equations, del f1 del y equals del f2 del x, it cannot be the gradient of a function. In our example, we had g of xy was equal to minus y comma x. And so this would be playing the role of g1, this would be playing the role of g2. And so if we take the derivative of g1 with respect to y, we get negative 1. If we take the derivative of g2 with respect to x, we get positive 1. And since those two numbers don't match, we know definitively that the vector field G is not the gradient of anybody. In comparison, the original vector field we looked at, f of xy equals xy, satisfied del f1 del y was equal to 0, and del f2 del x was equal to 0. These two numbers did match. And in fact, we found out that this function was the gradient of somebody. This last example should be kept with a grain of salt. All this test says is that unless the vector field satisfies these three equations, it cannot be a gradient function. It does not, however, say that just because a vector field satisfies the three equations, that it must be the gradient of something. This is a lot like critical points. This gives me a way of finding candidates for gradients, but I'd have to do more work. So why does the gradient test work? Well, let me give you a basic sketch of why this is true. Suppose that you did have a vector field, f, who took the form f1, f2, f3, and let's say that he was the gradient of some other function, so that his first component would be the derivative of f with respect to x, the derivative of f with respect to y, and the derivative of f with respect to z. So that would mean that f1 was fx, f2 would be fy, and f3 would be fz. Well, then what does this first equation actually say? The first equation would say that the partial derivative of f1 with respect to y, which is the derivative with respect to y of fx, which is just fxy, that should be the same thing as the partial derivative of f2 with respect to x. That would be the derivative with respect to x of the derivative of f with respect to y, and that would just be fyx. And so this equation right here is simply saying that fxy and fyx should be the same thing. But we already know that from our derivative information, as long as fxy and fyx are continuous. But that's what we just said in our hypothesis. We're saying that the derivatives of f are continuous. And so each one of these other equations is a similar statement. This boils down to the statement that fxz is equal to fzx. And this is just the statement that fyz is equal to fzy. So the gradient test is just restating the theorem of the equality of mixed partials, what was called Clairaut's theorem. Is the vector field f given by z squared plus 2xy minus 1, comma x squared plus z e to the y plus 2, comma xz plus e to the y, the gradient of some function f of z? This would be an excellent candidate for that gradient test. So let's first identify the pieces. This is the piece f1, this is the piece f2, and this last part is the piece f3. So the first of the three equations is del f1 del y equals del f2 del x. So let's work our way through this. Del f1 del y would be the derivative of this first equation with respect to y, which would be 2x. On the other hand, del f2 del x would be 2x again. So the first set of equations checks out. Del f1 del z against del f3 del x. So del f1 del z, if we differentiate this expression with respect to z, we're going to get 2z. If we differentiate del f3 with respect to x, then we're going to get z. And since these two values are not a perfect match, we know that the answer to this question is no. This is not the gradient of an unknown function. But what if we were to modify this example slightly? Let's go and say that the third component was a typo, and that it was actually supposed to be 2xz plus e to the y. In this case, the derivative of f3 with respect to x would be 2z, and the second equation would check out. So then we could test the third equation, del f2 del z, and see whether or not that's equal to del f3 del y. So del f2 del z, if we differentiate the second component with respect to z, we're going to get e to the y. On the other hand, if we differentiate the third component with respect to y, we're going to get e to the y. So all three equations check out. So what does the derivative test say? The derivative test says that the answer is... It can't tell me yes. It can just tell me no. But at least we know that this is a candidate for it. So how could we find whether or not there's such a function? What would such a function look like? Well, the gradient would have to take the form of fx, fy, fz, or these are little f's. So if this were to be the gradient, then the derivative of little f with respect to x would have to be this first component. That means that f would have to be the integral of z squared plus 2xy minus 1 with respect to x. So that would get us xz squared plus x squared y minus x. Plus constants. But what's constant with respect to x? Anything that has a y or a z in it. On the other hand, if the gradient of f were to match the given vector field, then the second components would have to match. So the partial derivative of f with respect to y would have to be the second component. That means if we integrate the second component, x squared plus z e to the y plus 2, with respect to y, then we would get x squared y plus z times e to the y plus 2y as an antiderivative, plus anything that involved just x's and z's, things that are constant from y's point of view. And similarly, integrating the third component would give us that f has to be xz squared plus z e to the y plus stuff involving only x's and y's. So, is it possible to find one f who can satisfy all three of these equations at the same time? Well, what would such an f have to look like? Well, it needs to have an xz squared term in it, and it needs to have an x squared y term in it, and it needs to have a negative x term in it to make the first equation happy. I've already counted an x squared y term. It better have a z e to the y term in it, and it better have a 2y term in it. I've already counted an xz squared term. I've already counted a z e to the y term. And so at a bare minimum, it needs to have these parts. Would such an equation work? Take its gradient and verify it. It's worth pointing out that this isn't the only f that would work. I could add any constant I wanted to it and not affect any of the data right here. What about integration of a vector field? So let's imagine that we had some kind of vector field, and I'm drawing it in the plane, but this could be a vector field in R3. So what would be the right kind of thing to integrate a vector field over? Well, one of the things that sort of define a vector field is that it has a sense of flow. The other thing that we've talked about this semester that has a sense of flow is a plane curve, something like this, where we have a starting point and a stopping point, and we have a directionality to it. So is it possible for us to take a vector field, like the one shown here, and to integrate that vector field over a curve as some kind of a line integral? Does this concept make sense? But what might we measure when we do something like this? Well, you might notice that at every point on this curve, there's two vectors worth considering. One of them is the vector f of x, which describes the vector field at that point. But there's a second vector at this point connected to the curve, and that would be the tangential flow vector, the unit tangent vector. And so at every point along the curve, there is a tangent vector who points in the direction of the flow of curve, and then there is a gradient vector that sort of points to the outside world. You might notice that sometimes the vector field and the unit tangent are pointing in roughly the same direction, whereas at other times they're pointing in opposite directions. So one of the things that we might measure is we might measure intuitively how much of the flow of f moves along the flow of c. What would that actually mean? Well, let me go and take one more point of this graph and sort of zoom in a little bit. So say we have the curve running this way, and we have our point. Now at this point, there's going to be a unit tangent vector who points in the tangential direction of the line, and is 1 unit long. There's also going to be some vector field vector right here. Now what we want to measure is we want to measure how much of this vector right here is moving in the direction that the curve is flowing in. Well, if you think about that, that's precisely the idea of projections. We're trying to figure out how much of this vector field is moving parallel or tangentially to the curve. And so this length right here is essentially a measure of how much this vector is flowing in the direction of the curve when f and t are pointing in the same direction, or potentially how much it's pointing in the opposite direction of the curve. Now you might remember that we had a formula for the parallel component of a vector for the projection, and that formula was to take the vector in question and to dot it against the vector you're projecting on, divided by the vector dotted with itself times the vector. But since t is a unit vector, t dotted with t is just 1. And so this will be f dot t times the vector t. And since all we want is the length of this, well, that just means we want to take f dot t. This value right here measures the length of this vector. And also notice that it has the property that it's going to be positive if f and t are pointing in the same direction, and negative if f and t are pointing in opposite directions. And so this is going to be our integration concept. We're going to go and take f dotted with t, which is a real valued function of two variables, and then compute its line integral over the curve c ds, since we know how to compute line integrals for real valued functions. What if we'd actually gone through and parameterized this particular curve with a vector valued function c of t, where the beginning point happens at time equals a, and the ending point happens at time equals b? From the previous lecture, we know that this would be solved as the integral from a to b of this expression evaluated at c of t, so we'd have f of c of t dotted with t of c of t, times the speed function, which is the derivative of c prime of t magnitude, dt. But you might remember that we had a formula for computing the unit tangent to a curve. Do you remember what that formula was? The unit tangent was the velocity divided by the length of the velocity. It was the velocity vector normalized. But remember that the velocity of a curve is nothing more than its derivative. So this expression can be rewritten as velocity, the derivative of the curve, divided by the length of the derivative of the curve. Well, in this case, these two speed statements cancel, and so we're actually left with the simplified formula of the integral from a to b of f of c of t dotted with c prime of t dt. This is sometimes called the vector line integral of f over c. And the symbol that we usually use, or the symbol that's used to denote it, is the integral of f dotted with ds, with a little arrow over the top. The symbol is chosen to remind us of two things. First off, that we have a dot product, and secondly, it's supposed to remind us that the flow of the curve has meaning this time around. If we were to take the same curve in this picture, but assumed instead that the flow went in the other direction, then all of our unit tangent vectors would be pointing in the opposite direction, and that would have the effect of changing the sign of this dot product. Compute the vector line integral of f ds over L if f is the vector field x, 2y, and L is the line from the point 0, 1 to the point 3, 3. So our formula for this vector line integral is just going to be the integral from a to b of f of c of t dotted with c prime of t dt, where c is any parameterization of this line. Now let me draw a quick picture right here. This is a line who starts at the point 0, 1 and then goes to the point 3, 3. We can write the parametric equations of such a line easy. It starts at the point 0, 1, and then the vector who runs parallel to this, well, if I take tip minus tail, would be the vector 3, 2. And so, plugging in this, the parametric equations x equals 0 plus 3t, y equals 1 plus 2t would describe the line. So we could make a parametric equation, c of t is equal to 3t, comma, 1 plus 2t. And then we need only find the times when this event occurs. Well, when time is equal to 0, we're at the starting point, and when time is equal to 1, we're at the ending point. And so time will go from 0 to 1. So now we have all the information we need to plug into here. Well, let's go and work out each of the components, kind of like how we did with a line integral. What would f of c of t be? Well, f of c of t would be x comma 2y, except that we'll replace x and 2y with their vector components. So this would be the vector field 3t comma 1 plus 2t. On the other hand, c prime of t, that's just going to be the derivative of our parametric equation, which is 3 comma 2. And then last but not least, we need to work out the dot product of these. So if we take this vector dotted with this vector, well, let's see. If we take 3t, 1 plus 2t, and we dot it with the vector 3, 2, we're going to end up with 9t plus 2 times 1 plus 2t. That would be 9t plus 2 plus 4t, or 13t plus 2. And so this becomes the integrand, and our calculus problem becomes the integral of 13t plus 2 dt evaluated from time equals 0 to time equals 1. And so now we're back to Calc 1. If we find an antiderivative, we get 13 halves t squared plus 2t evaluated from 0 to 1. That will get us, plugging in 1, 13 halves plus 2, plugging in 0 will get us 0. And so that gives us a grand total of 17 halves as the line integral. Compute the vector line integral of y minus x squared I plus z minus y squared j plus x minus z squared k dot ds if c is parameterized by the vector valued function r of t is ti plus t squared j plus t cubed k. So in this case, notice that our vector field is written right here in standard basis form. Just to make it a little bit more obvious here, the vector field in this problem is y minus x squared, z minus y squared, and x minus z squared. And the curve that we're integrating over has actually been pre-parameterized for us by the equation t squared, and t cubed. So we have all of the facts we need to integrate this. To work out the integral of this vector field dotted with ds, we simply need to go and work out f of r of t, in this case, dotted with the derivative r prime of t dt, and we evaluate this from the starting value t equals 0 to the ending value t equals 1. So let's work out each of these individual pieces. First off, f of r of t. So f of r of t, that's just going to be f of the point t squared, t cubed. And so we're going to have y minus x squared, z minus y squared, and x minus z squared. So that will give us the vector field 0, t cubed minus t to the 4th, and t minus t to the 6th. Next, we need to work out the derivative of r. So the derivative of r prime, will just be the vector 1, 2t, and 3t squared. And finally, we need to work out their dot product. Well, here's the two vectors. If we simply dot them together, we're going to get 0 times 1, which is 0, plus 2t times t cubed minus t to the 4th, plus 3t squared times t minus t to the 6th, or 2t to the 4th minus 2t to the 5th, plus 3t cubed minus 3t to the 8th. And so this is the integrand we need to work with. So if we plug that in, we need to integrate from 0 to 1, 2t to the 4th minus 2t to the 5th, plus 3t cubed minus 3t to the 8th dt. Well, this is now a standard calc problem, so let's just go and grind it out. Anti-differentiating each piece separately, we're going to get 2/5 t to the 5 minus 2/6 t to the 6th plus 3/4 t to the 4th minus 3/9 t to the 9th, evaluated from 0 to 1. So if we plug in time equals 1, we're going to get 2/5 minus 2/6 plus 3/4 minus 3/9. If we plug in 0, we're just going to get 0. And so that'll give us the following three fractions added together. If we put that on a common denominator, we're going to end up with 29/60ths. So just a smidge under a half. Because the line integral of a vector field is defined in terms of the line integrals of ordinary functions, a lot of the properties of line integrals from yesterday will carry over to properties of line integrals today. For example, the line integral of a vector field ds over some curve C is independent of the parameterization used to compute it. The line integral of a scalar multiple of a vector field is that multiple of the line integral of the vector field. The line integral of a sum of vector fields is the sum of the line integrals of the individual vector fields. If a certain curve can be split into two subcurves, then the line integral over the total curve is the sum of the line integrals over each of the two smaller curves. Unfortunately, the fifth property of line integrals from yesterday doesn't carry over. The directionality of a curve does matter. We saw that for line integrals over functions, the line integral was independent of the directionality of the curve. It didn't matter whether you parameterized the curve from, say, left to right versus right to left. However, for line integrals, it does make a difference. These are vector-valued things, and vector-valued things have, well, direction. However, there is an easy fix. If you integrate a function over a curve in the opposite direction, then the line integral isn't the same, but it will be the opposite of the line integral you get in the other direction. This is in some sense the analog of the Calc 1 notion that if you integrate from A to B, or you integrate from B to A, one of these is the opposite of the other. And so these form the basic properties of vector line integrals. Because of the difference in property 5, we often distinguish between the line integral of a vector field and the line integral of a function by calling the line integrals of vector fields vector line integrals, but the line integrals of functions scalar line integrals. Another piece of notation that's sometimes used is as follows. If the vector field f has components u and v, and the curve C is parameterized by the vector-valued function c of t equals x of t, y of t, then the vector line integral takes the form of f of c of t dotted with c prime of t dt evaluated from one point to another point. Now let's write what this thing actually is, kind of in the process we've done before here. F takes the form of uv, c takes the form of the derivative of x dx dt, and the derivative of y dy dt. So if we work out this dot product will be u times dx dt plus v times dy dt dt. Now if we imagine for just a second that we could distribute this dt, this integral would take the form of the integral of u dx plus v dy. And so if we simply replace the time a to b with the original curve c, then this notation is also sometimes used to denote a vector line integral. This is sometimes known as the scalar differential form of a line integral, and it's just another competing notation with this one right here. The nice part about this notation is it allows you to encode the vector field really naturally in the integral itself. Compute the line integral of 3dx plus xy dy over c, where c is shown below. So notice that this problem is simply setting up to say that the vector field f is the vector field 3, xy, and that c is this shape right here. Well, if I look at c, I notice that it sort of breaks down into two sort of easier pieces. There's this piece c1, who lives on the curve y equals x cubed, and then there's a piece c2, who lives on the curve x equals y cubed. And so to work out this line integral, the line integral over c, I can break this up into the line integral over c1 plus the line integral over c2. So let's work these out in smaller pieces. Let's focus on the line integral over c1 first. Now notice that c1 can be parameterized by the equations x equals t and y equals t cubed, since I'm on this particular line. When time is equal to 0, we'll hit the point 0, 0. What about this place where these two curves meet? Well, we could solve that really quickly by setting the two equations equal to each other. We have y is equal to x cubed. On the other hand, the second equation is the same thing as y is equal to the cube root of x. So if we set these equal, we get x cubed is equal to the cube root of x. If I cube both sides, x to the 9th is equal to x. And so that means that 0 is equal to x to the 9th minus x. That's x times x to the 8th minus 1, which means that either x is equal to 0 or x to the 8 is equal to 1, which means that x is equal to plus or minus 1. So these two curves meet at 3 points, at x equals negative 1 down here, at x equals 0, the origin, which is obvious, and also at the point x equals 1. But if x is equal to 1, then these two equations say that y is equal to 1. Now notice that when time is equal to 0, we manage to hit this first point, and when t is equal to 1, we'll hit the second point. And so we could parameterize this first equation for the values t going from 0 to 1. So let's work out this first line integral. The line integral over c1 is going to be the integral of 3 dx plus xy dy evaluated from 0 to 1. Well, let's make all of the correct substitutions. What is dx? Well, dx is just going to be the derivative of x, which is 1 dt, plus x, y, times the derivative of y. Well, the derivative of y is going to be 3t squared dt. And so this will be, if I clean this up a little bit, 3 plus 3 times t to the 6th dt, evaluated from 0 to 1. So if we integrate that, we're going to get 3t plus 3/7 t to the 7th, evaluated from 0 to 1. That means we're going to have 3 plus 3/7 minus 0, or 24/7. And so that will be the contribution from the first integral. Now let's focus on the second integral. Notice that the second curve, the curve C2, is on the curve y equals the cube root of x. Now it's easy to parameterize the graph of a function by setting x equal to t and y to be the corresponding function value evaluated at t. So we have x is equal to t, y is equal to t cubed. When time is equal to 0, we're at the bottom point. When time is equal to 1, we're at the top point. So this description right here, x equals t, y equals t, where t goes from 0 to 1, describes the right shape, but it has the wrong direction. It's going from left to right, whereas we need it from right to left. But we can use one of our cool properties. Our cool property number 5, said that the integral of C2 is just going to be the opposite of the integral of negative C2. And that's what we've parameterized. We've parameterized C2 in the opposite direction. So we can go and now use our parameterization given right here, and we'll just keep this extra negative floating out in front. So we're going to have negative the integral of 3 dx plus xy dy evaluated from 0 to 1. And we're going to plug in this new parameterization. So minus the integral from 0 to 1 of 3 times the derivative of x, which is 1 dt, plus x times y, which is t to the 1/3, times the derivative of y dt. Now the derivative of y is going to be 1/3 t to the minus 2/3 dt. So if I pull out the dt's, we're going to have 3 plus 1/3 times t to the first times t to the 1/3 times t to the 2/3, which is t to the 2/3 power dt. Anti-differentiating that will get us 3t plus 1/3 times t to the 5/3 times the power of 3/5, or 1/5 t to the 5/3 power, evaluated from 0 to 1, and I can't forget that there's the negative out in front right here. So keeping the negative out in front, when we plug in 1, we're going to get 3 plus 1/5, minus negative, when we plug in 0, we're going to get 0, and so that will get us negative 3/5, so that will get us negative 3 1/5, or negative 16/5. So the second integral contributes a negative 16/5. If we put these values on a common denominator, we're going to come up with 8/35. And so there's our line integral.